Hello everyone. So let's solve a Leetcode problem today, and this is problem 210, course schedule 2. This is similar to another problem, obviously course schedule 1, which is problem 207, and problem 207 is one of the blind 75 problems. So if you solve like any of these two, actually you're fine. So only difference is here you have to so the output is just different. So in one of the outputs you create a list, return the list. In the other output you just return the size of the list, something like that. Okay, so let's solve this problem 210. And so the problem statement says there are a total number of num courses labeled from 0 to num courses minus 1. That means suppose there are like 8 courses. So the course name are labeled as 0, 1, 2, 3, 4, 5, 6, 7, right? So if there are 8 courses, the courses are labeled from 0 to course number minus 1. You are given an array prerequisites where the prerequisites I is a pair. AI and BI indicates that you must take course BI first if you want to take course AI. Okay, so if there is a element like this, that means to take course 1, say course 1, yeah, you must take course 0 first. Okay, so that's the definition of the prerequisites. You also know about this probably. And we have to return the ordering of the courses. You should take to finish all courses. If there are many valid answers, return just any of them. It is impossible to finish all the courses. If it's impossible, okay, so that means we are given the courses and then we are given the prerequisites, okay, something like this. And then we have to return an ordering saying if we take the courses in this order, we can finish all the courses. Okay, and if we cannot finish, in that case, we have to return an empty list. So here is one example. Say in the first example is a second example. Let's look at the second example. So the number of courses are like 4. That means the course labels are 0, 1, 2, 3, and the prerequisites are like this. That means to take course 0, I have to take course 1 first. To take course 0, I also have to take course 2 first. To take course 1, I have to take course 3. And to take course 2, I have to take... oh, okay. So probably I made a mistake. So, okay. So as per the definition, okay. So if I want to take course A1, I first have to take course B1. Okay, so I made the mistake. So if I want to take course 1, I need to take course 0 first. Also, if I need to take course 2, I have to take course 0 first. To take course 3, I also have to take course 1. To take course 3, I have to take course 2. Okay. And then after that, I have to return an ordering, that which order is a valid order. I can take the courses so that all the prerequisites are met, etc. And I also have to make sure that I can take all the courses 0, 1, 2, 3. Okay, so let's try to solve this problem. So this one, we have to return an ordering. So this looks like a topological sorting problem. So let's define this as a graph. So the nodes of the graph are 0, 1, 2, 3, right? That is the nodes of the graph. So let's draw them. Say 0, 1, 2, 3. Okay, there are 4 nodes. Say there are 4 nodes. And these are the courses, right? And then this graph has some edges. edges are 1 0, 1 0, 2 0, 3 1, 2 3 2. So these are the vertices, right? And the edges are like 1 0, 2 0, 3 1, and 3 2. Okay, and these are directed edges. That means to take course 1, you have to take course 0. That means 0 is a requirement for 1. Okay, after you take 0, you can take 1. To take course 2, you also have to take course 0. So 0 is a prerequisite to 2. To take course 3, we have to take course 1. That means 1 is a prerequisite to 3. And then to take course, and 2 is a prerequisite to 3. Okay, so this is our graph. Now we have to find a valid ordering so that everything is done. So to do a topological sort, we know that we can do it using a variation of BFS. So before that, what do we need is, let's define this as, so we start with a course which doesn't have any dependency. For that, we need an array. Say we call this an in-degree array, right? So this is an in-degree array. In-degree means the number of incoming edges in an array, right? And this is the index 0, 1, 2, 3. Okay, let's see. Index 0 doesn't have any incoming edges. That means its in-degree is 0, right? Course 1 or node 1 has one incoming edge. So the in-degree is 1. Course 2 has one incoming edge, in-degree is 1, sorry. Course 2 has one incoming edge, so in-degree is 1. And course 3 has two incoming edges, so the in-degree is 2. Okay, so this is the in-degree. And this is important because the course that has an in-degree of 0 can be taken right away, because that means it doesn't have any dependency, right, on any other course. The next thing is we need a queue, right? We need a queue where we will put the courses that can be taken, right? So from here, we can see that we can take course 0. And this is the ordering list. So in the ordering list, what we do is we have to put, like, take out from the queue and put in the ordering list, right? Okay. And once we take something out, we have to look at the neighbors and then change their in-degree. So for neighbors, we have to keep a list. So we are familiar with adjacency list, right? So we can, since this is a graph, and if we need to find the list of the neighbors from the graph, either we use adjacency matrix or adjacency list. So let's create an adjacency list from these edges. Okay, so the adjacency list will look something like this. So this is for node 0, this is for node 1, this is for 2, this is for 3. This one has a list. Okay, so what are the neighbors of 0? You see the neighbors of 0 are 1 and 2, right? And you can see here from the graph as well. But the neighbors of 1, one's neighbor is 3. You see that? One's neighbor is 3. So this is 3. 2's neighbor is also 3. And 3 doesn't have any neighbor, so it's an empty list. Okay, so initially we said that the in-degree of the course that doesn't have any dependency or anything goes into the queue. That is course 0. And then we want to take this out. So before we take this out, what we have to do is we have to look at the neighbors from this list. The neighbors are 1 and 2, right? So we have to remove, taking course 0 means that I am taking the course 0, I am taking it out of the queue, putting it in the ordering, looking at the neighbors, and I have taken the course 0. That means the dependency 1 and 2. Now I am free to take 1 and 2. So we need to reduce the dependency of course 1 and 2. So the dependencies from 1, it goes to, is subtracted by 1 or reduces by 1. So both of these goes to 0. And we know that as soon as a course has no more dependency, that means the degree becomes 0, we put them in the queue, right? We don't put all the neighbors in the queue. The neighbors that has an updated in degree of 0 goes into the queue. Okay, so next time I take one out, put it in the ordering. Now I look at the neighbors of 1. What is the neighbor of 1? 3, right? Okay, so I go there into 3, reduce the in degree by 1. Now the new in degree becomes 1. Okay, so what happens is, although I reduce the in degree of 3 to 1, it doesn't, I don't put it in the queue. I don't put 3 in the queue because queue is not, I'm not free to take course 3 because course 3 still has some dependency. Okay, so next I take out course 2, put it in the ordering, I look at the neighbor of 2, which is 3, and sorry, this one I had to remove. Okay, I look at neighbor of 2, which is 3. I remove the dependency. So the in degree now from 1, it goes to 0. Okay, and once it goes to 0, immediately I can put it into my queue. Okay, next I take 3 out. Now I see that obviously 3 doesn't have any neighbors, so I don't need to do anything. The final thing is I will check if the size is equals to, the question is the size is equals to number of vertices. If the size is equals to number of vertices, that means that I am able to take all the courses, right? If that is if that is true, if true, then I return this list. Otherwise, I return a new empty list. Okay, so let's try to code this. Okay, so I need an array, call it in degree. This will actually keep track of dependent, or keep track of number of prerequisites. Sorry. And the size of the array is going to be the size of the number of courses, right? Okay, and then I keep a list. For the adjacency list, I have to keep a list of lists, right? So, and the courses are labeled by integers. So let's call it AL, adjacency list. There's a list of lists. Okay, and then we need a queue for my modified BFS, right? So the queue also will have integer. We know that the queue is an interface, so we have to use an implementation class of it, which is linked list is one of the implementation classes of queue. Okay, so so that is it. And then now let's populate the in degrees of each courses. So for that, what I have to do is I have to go through each edge. Okay, so when I'm actually looking at the edges, I can do two things together. I can build the adjacency list, and then I also can populate the in degree array. Okay, so let's do this. For adjacency list, what I do is initially I create an empty list for each of the nodes or each of the courses. So l dot add new array list. So, okay, so if there are like, depending on the number of courses, I'm creating that many empty arrays and adding them to the list. So it's like this. So creating this and then creating empty, so creating the list, and for each entry, I'm just creating one empty list, right? And then we'll populate these empty lists. Okay, so that is done. And what I do is also for in degree of, you know that if the array is like this, if the edge is like this, 1, 0, right? Oh, okay. So for that, actually, I need to do it later. Okay, so I create empty list for the adjacency list, and then I go through the edges or the dependencies. Let's call it prerequisite. So I will iterate through the prerequisite or the edges, and you know that if there is something like this 1, 0, that means 1 is dependent on 0. That means the first element is dependent on the second element. So what I have to do is I have to increase the in degree of the second element. Sorry, in degree of the first element, right? Yeah. And then the first element becomes a neighbor of the second element, right? Okay, so this is like this. Since there was a link edge between 0 to 1, the in degree of 1, like this one, went by 1, up by 1, and 1 was also added to the as the neighbor of 0, the second element. So from the adjacency list, I get the second element, adjacency list of the second element, which is 1, and then add to it the first element. Okay, so I'm creating, populating the in degree and also populating the adjacency list. Okay, so I'm done there. And now what I do is I have to run a for loop since I am done with, so creating the in degree list. Now I have to put the nodes that has in degree of 0, right, into the queue. If in degree of I equals to 0, q dot add I. Okay, so that means I have added to the queue all the nodes or all the courses that are not dependent on anything. Next, I have to run the BFS thing while queue is not empty. Well, queue is not empty. What I have to do is I have to take one course out of the queue and add it to the result. So here is the thing. You know, the ordering is going to be, the ordering array is, the size of the ordering is going to be maximum of number of courses, right? So we can actually keep an array. Okay. And then also in the ordering array, in every location I have to put the course number, right? So this is the index of the ordering array. So what I do is I take one element out of the queue. And then in the ordering array, this is the first course, right? I assign it as course J. This is the first course I can take. And then what I do is I increase it by 1 because next time I will be looking for the second course. And once I am taking this out, I have to check all the neighbors, right? So I can get all the neighbors from here. So I can do this for adjacency list dot get the J. Okay, so I will get each of the arrays and each of the neighbors, and for each of the neighbors I have to reduce the in degree by 1 because I already have taken course. That means I'm taking it out of the queue. That means I have taken this course, added it to the ordering, and then I am going through the neighbors of that course and reducing their in degree by 1. Okay. So next time I will be looking for the second course. Then I will be looking for the third course, right? I will keep on doing this until the queue is empty. Okay, so once the queue is empty, then I have to check if this array is full, right? If this is full, or I can check this. That is the case. That means I already have reached here. If I equals to if this is the if it is not true, that means I couldn't take all the courses. That means obviously there was a cycle in the graph. So I have to return an empty list, right? I just return an empty list. Say a list of size 0. Otherwise, I'll return the ordering array. Okay. So let's try to run this. Okay. So this is wrong. That is fine. Oh, okay. So I made a mistake here. You see that? I just added the in degree, but I also have a big mistake. If the in degree becomes, after reducing it, if the in degree of the neighbor becomes 0, I have to add them to the queue. Big mistake. Yeah, because so that means all the dependencies for this course K has gone. So I have to add it to the queue. Let's try to run this. Yeah, now it's accepted. Yes. So okay. So now let's see what is the time complexity of this algorithm. So doing this is order of V, number of vertices. Doing this is order of E, right? This is dependent on the number of edges. This is also order of V, right? Number of courses. And then how many times we are doing this? Now you see that in the queue, you're pushing at most V times the number of courses. And also for each of the courses, we're looking at its neighbors. And the total number of neighbors are going to be E. That means number of edges, right? Depends on the number of edges. That means eventually the time complexity of the algorithm is going to be order of V plus order of E. And that is the time complexity of a topological sort. Okay, so in the total amount of work is order of V plus order of E. And space complexity is, we have used some extra space. You see it here, like we have used the space for the ordering, the in degree. These two are like order of V space, right? And then we have put a queue. In the queue, the maximum number of elements that can go in is order of V. That is order of V. And finally, the number of edges. So the size of the list is going to be in adjacency list. We don't waste any space, and the size of an adjacency list is order of E. That means the space complexity. So the time is this, and the space is also going to be order of V plus order of E. Okay. So if it's a sparse graph, then E is much less than, or E is not much bigger than V. If it's a dense graph, then E can be almost order of V square. Anyways, this is the time complexity and the space complexity. So thanks for watching. We'll come back with another problem next time.